AP Physics 1, Unit 8, Lesson 2. In this lesson, we're going to continue our look at rotational motion, and we're switching from kinematics to now dynamics, which means forces and Newton's laws of motion. So just as I've said quite a few times, it's the same concepts, just different symbols. So we're going to move from our old F equals ma, and we're going to find the rotational equivalent for each one of those variables, and then we're just going to continue to move forward, and we'll take a look at what's different about that formula in class, but in this lesson we're going to take a look at the individual pieces. So force is going to be replaced by torque, mass is going to be replaced by moment of inertia, and acceleration is going to be replaced by angular acceleration. And what all three of those terms have in common is that they're linked to their linear counterparts by the radius. Radius is always the link between the angular and the linear quantities. And also the good news is we've already talked about angular acceleration with kinematics, so we're going to narrow our focus in this lesson on torque and moment of inertia. So what is torque? Torque is a force applied at a moment arm. So it's not just looking at the force, but it's also looking at the moment arm or the radial arm or the lever arm. Those are all three terms for the same thing. And the radial arm is the perpendicular distance from where the force is being applied to the pivot point. So if we think about opening a door, we apply a force to the door and the pivot point is at the hinge. Well, the radial arm is the perpendicular distance from the hinge to that force. So if we apply a force that's closer to the hinge versus a force that's farther away from the hinge, the one that's farther away from the hinge applies a greater torque. It's much easier to open a door if you're pushing at where the handle is located versus close to where the hinge is located. So the larger the radial arm, the greater the torque. So that's why we use tools such as wrenches. The longer the handle on the wrench, the more torque that you can apply. So even if you're not as strong as somebody else, you can apply that force to a longer radial arm and you can still get the job done. So that's why we have these tools, which are levers, like first, second, and third class levers, which you may have learned about back in 9th grade. So what happens when you're applying a force at an angle? So instead of that force being at 90 degrees to the radial arm, you now have your force at some angle theta. Well, we kind of looked at a similar situation, although it's not going to be exactly the same. But when we talked about work, we talked about the fact that when you had a force that was producing work, the force had to be in the same line of motion as the displacement. Well, that's known as a dot product. Torque is actually known as a cross product. So in this case, you want the force to actually be at a 90-degree angle from the radial arm. You don't want any part of your force to be in the same line as the radial arm. So what that means is when you look at this force that's being applied at an angle theta, there's two components to this force. There's a y component and there's an x component. The x component is acting in the same line as the radial arm, and it's acting directly into the hinge. So that force is not going to produce any torque. It's not going to assist you in opening up that door because it's acting directly into the hinge. You can try this. Stand at the edge of a door and push directly into the edge of the door toward the hinge. The door is not going to go anywhere. But the component that's perpendicular, the one that's in the y direction, this component is going to produce torque. So oftentimes you're going to see the torque equation as RF sine of theta, and this theta is supposed to be the angle between the radial arm and the force. Now again, do not use this equation blindly. So make sure that your force, whatever component of the force that you have, and the radial arm are at 90 degrees to each other. That's what you're looking for. So we'll get into examples, especially when we talk about static equilibrium, where you're going to have to account for this, and you're either going to have to find the components of the force, or you're going to have to find the components of the radial arm, the distances, in order to get the radial arm. So again, the force and the radial arm need to be at 90 degrees from each other. Now also from this equation, torque equals RF sine of theta, you can also get the units for torque. Oftentimes you're going to see the units written as a Newton meter. So force is measured in newtons, radius is measured in meters. However, the more appropriate unit is actually a meter Newton. And this comes from the fact that torque is a cross product. And for anyone who knows anything about unit vectors, you probably don't really know much about unit vectors, but if you take the C course, you will. The R must come first. So you will see this also written as a meter Newton. For me, it doesn't really matter. If you put a Newton meter or a meter Newton, it's okay. So let's take a look at a practice problem involving the basic definition of torque. So we have two mechanics that are both pulling on this very large wrench, and we need to find the net torque that the two mechanics are applying in order to loosen this screw. So I would first start by drawing a picture of the problem. Here we have these two forces acting on the wrench. One is being applied at the end, but it's at 80 degrees. The other one's being applied halfway across the wrench, and it's being applied at 90 degrees. So when you add together the torque by the two forces, you get an answer of 742 meter newtons, or Newton meters, whichever you prefer. Now at this point I need to talk a little bit about direction. And this goes to something called the right-hand rule, and I'll talk a little bit more about this in class. But the right-hand rule would dictate that counterclockwise torques are positive and clockwise torques are negative. So again, counterclockwise torques are positive and clockwise torques are negative. So the way that I have this drawn, both of these forces would be causing the wrench to rotate in a counterclockwise direction. So both of these would add up to be a positive torque. Again, for this problem, it really depends on how you drew the picture, but the way I have my picture drawn, it would be a positive 742 meter newtons. The second concept we need to talk about in this lesson is a concept known as moment of inertia. And moment of inertia is the rotational equivalent of mass. When you're looking at rotating objects, not all pieces of mass are equal. The farther a piece of mass is from the axis of rotation will give it a greater weight when looking at the rotational motion. So certain things like angular momentum, kinetic energy, rotational kinetic energy, these will all be affected by where that mass is located. So that means that we can't just talk about mass, but also the location of the mass from the axis of rotation. So that's what moment of inertia takes into account. So the very general form of moment of inertia is the factor of m times r squared. So for a particle, an individual particle, the moment of inertia is going to be equal to mr squared, where m is the mass of the particle and r is its location from the axis of rotation. Now, if you have more complex shapes, they are going to have different factors in front of this. Now, we don't get the fun job of actually deriving where these relationships come from. That we leave for the C course. But you must be aware that there are different moments of inertia for different shapes. And you should be aware of some of these relationships and actually know some of these relationships. I would probably be aware of the thin hoop, the solid cylinder, which can also be referred to as a solid disc, the sphere, and the long uniform rod with the axis of rotation through the center and also through the end. So please be aware of that, and you need to be able to use these moments of inertia. So let's take a look at a very simple example, finding the moment of inertia of a system of particles. So we have 4 particles, and the 2 larger masses, m, each have a mass of 5 kilograms, and they are 1.5 meters away from the axis of rotation. You have 2 smaller masses, which are 2 kilograms, and they are a distance of 1 meter away from the axis of rotation. Now, moment of inertia is a scalar quantity, just like mass. So that means if we find the moment of inertia of each individual piece, we can just add them all together. We can just sum them up to get our moment of inertia. And when we go ahead and calculate the moment of inertia, we have 2 of the larger masses plus 2 of the smaller masses, and our total comes out to be 26.5. And the unit on moment of inertia, again, it's not a pretty unit, but it comes directly from the relationship. So it's mass times radius squared, so we have kilograms times meters squared as our unit. And this is the end of Unit 8, Lesson 2.